Okay, so picture this. It's a few hundred years ago, and everyone's totally convinced that the Earth is the center of everything, like it's some cosmic VIP.
It's totally understandable, though, right? Think about it. Back then, all they had were their eyes. No fancy telescopes or anything. It's like trying to figure out how a car engine works by just looking at the outside.
Yeah, makes sense. But then there's Ptolemy, right? He comes up with this whole system of epicycles, like those little wheels on a toy train, to explain why planets sometimes look like they're moving backward.
And get this, that model stuck around for over 1,000 years. It shows how even when our ideas aren't quite right, they can still be like stepping stones to something bigger.
It's like those early versions of software, right? They're a bit clunky, but you got to start somewhere. Speaking of major upgrades, let's talk about the heavyweights who totally changed the game. Newton, Maxwell, and Einstein.
Newton's law of gravity. Total game changer. And it wasn't just about explaining why planets move in those elliptical paths like Kepler figured out. This law gave us the inverse square law, this principle that pops up everywhere in physics.
Wait, so it's like this secret code that unlocks not just gravity, but other forces too.
You got it. It's all about finding those hidden connections. And you know what's mind-blowing? Newton realized that the same force that makes an apple fall is what keeps the moon in orbit around Earth.
That must have blown everyone's minds back then.
It did. It was huge. And Newton, he didn't stop there. He went on to prove that if you've got a perfectly round object, like a planet or a star, you can act like all its mass is packed right at its center when you're calculating gravity.
Talk about attention to detail. Reminds me of this guy, Heaviside, brilliant physicist, but kind of a loner. He was all over Maxwell's work, even though Maxwell himself wasn't always super clear about the details.
Heaviside, he just got it. He saw the elegance in Maxwell's equations, how they brought together electricity and magnetism, and even predicted these things called electromagnetic waves.
Which we confirmed later with Hertz's experiments. That back and forth between theory and experiment is what really pushes science forward, wouldn't you say? Speaking of breakthroughs, what about Einstein? And that whole thing with light always moving at the same speed, that's where things start to get really weird for me.
So picture this. You're racing a beam of light. Doesn't matter how fast you go, the light's always moving away from you at the same speed. It's like it's playing a cosmic joke, right?
Yeah, totally. Like, how is that even possible?
Einstein realized that for this to work, we got to throw out the idea that space and time are these fixed, unchanging things. He said they're woven together like this fabric called space-time. And gravity. It's not some mysterious force acting at a distance. It's the warping of this fabric.
Okay, so space and time are like this giant flexible sheet that can be bent and twisted. And we experience that bending as gravity.
Exactly. It's a mind-blowing concept, but that's Einstein for you. He was a master of connecting things that seemed totally unrelated. And, you know, while he was working on all this relativity stuff, he also tackled something called Brownian motion. Ever notice how dust particles seem to dance around randomly in the air?
Yeah, like they've got their own little groove going on.
Einstein figured out that this was actually evidence of atoms randomly bumping into the dust particles. Back then, the whole idea of atoms was still up for debate.
Wow, so he was juggling multiple scientific revolutions at the same time. Okay, so we've got this flexible space-time, but then we enter the truly bizarre world of quantum mechanics. It all started with Planck trying to figure out why hot objects glow the way they do.
Classical physics had no good answer for this, but Planck, he had this radical idea. What if energy isn't this smooth, continuous flow, but comes in tiny little packets, like discrete bursts?
Like those individually wrapped candies instead of a whole bag of loose ones.
Perfect analogy. Those little packets, we call them quanta. And the size of each packet, determined by Planck's constant, a fundamental constant of the universe.
It's like the universe has a set of Lego blocks, and Planck figured out how big each block is. Then comes Niels Bohr, who takes this quantum idea and applies it to atoms. He was trying to explain those weird spectral lines, those unique colors you see when you burn different elements.
Yeah, Bohr, he wasn't the most exciting lecturer, but his model of the atom, with electrons hopping between these specific energy levels, was revolutionary.
So instead of those electrons smoothly orbiting the nucleus like planets around a star, they're making these quantum leaps between energy levels. That's what gives us those distinct spectral lines. But this is where quantum mechanics starts to get really strange, right? Particles acting like waves, things existing in multiple states at once.
Exactly. The rules of the game completely change at the quantum level. It's like suddenly the chess pieces can be in multiple places at once.
Definitely makes for a more interesting game, but also makes my brain hurt a bit. And then there's Feynman and his whole path integral approach. It's like he's saying a particle doesn't just take one path, it considers every possible path at the same time.
It's like the universe is a choose-your-own-adventure book, and the particles are reading all the endings simultaneously.
And to make it even weirder, we have these phenomena like superfluidity and superconductivity. It's like matter throws a party and forgets to invite the laws of physics.
It's more like those laws get rewritten at extremely low temperatures. We call it broken symmetry. When that happens, you get these totally unexpected behaviors, like liquid helium flowing without any resistance. It's like magic, but it's quantum magic.
So the universe has these hidden rules, and they only come out to play under extreme conditions. Okay, we've gone from atoms to quarks, but how did we even get there? Tell me more about this standard model of particle physics.
It's like this. Remember that whole Earth-centered universe idea? We zoomed out to the solar system, then the galaxy, and now we're going even smaller, into the heart of matter itself.
It's like those Russian nesting dolls, but instead of dolls, it's particles within particles.
Exactly. And one of the coolest parts of the standard model is the electroweak theory. It combines electromagnetism and the weak forcifor. Two forces that seem totally different, but are actually connected at a deeper level.
It's like finding out that rock and roll and classical music actually have a common ancestor.
Precisely. It's all about uncovering that hidden unity.
Okay, so we've got electromagnetism and the weak force teaming up. But what about that strong force, the one holding those quarks together inside protons and neutrons? That always seemed like the really strong, silent type.
Yeah, the strong force is a bit of an enigma. It's governed by this theory called quantum chromodynamics, QCD for short. And it has this weird quirk called asymptotic freedom.
Asymptotic freedom. Sounds like something you learn in a philosophy class.
It's actually pretty straightforward once you wrap your head around it. Imagine you're trying to pull two quarks apart. The farther apart you pull them, the stronger the force between them gets. Like they're connected by this super strong rubber band.
So the more you try to separate them, the more they want to stick together. That's kind of how I feel about some of my friends.
Exactly. But here's the really weird part. If you get those quarks incredibly close together, almost on top of each other, the force between them actually weakens. They become almost asymptotically free.
So it's that they're claustrophobic quarks. They can't stand being too close to each other.
In a way, yes. It's this really counterintuitive behavior that makes studying quarks in isolation incredibly tricky. They're always bound together by this incredibly strong force.
Sounds like a recipe for a headache for physicists. So the standard model, it's great at explaining a lot, but it still has some gaps, right? Like finding a way to bring gravity into the mix to unify all the forces into one elegant theory.
That's the holy grail of physics, isn't it? A theory of everything. Einstein himself spent years searching for a unified field theory, but even he couldn't quite crack the code.
So what's the holdup?
Well, the way we understand gravity through general relativity, with space-time being this flexible fabric, it's just really different from how we describe the other forces in the quantum world.
It's like trying to solve a jigsaw puzzle, where half the pieces are from a completely different puzzle.
That's a good analogy. But physicists, they love a good challenge, and that's where string theory comes in.
String theory.
Mm-hmm.
I've heard of it, but it always seemed kind of out there, like, what are those strings even made of?
Okay, so instead of picturing particles as these tiny points, imagine them as these tiny vibrating strings. And just like a guitar string can produce different notes depending on how it vibrates, these strings can vibrate in different ways to create all the different particles and forces we observe.
Wait, so instead of a whole orchestra of different particles, we've got this one string section that can play all the notes.
Exactly. It's all about those different vibrational patterns. And what's really cool is that string theory naturally includes gravity. It even predicts the existence of this particle called the graviton, which would be the force carrier for gravity.
Okay, I'm starting to see why people get excited about string theory. But I've also heard it involves extra dimensions. And not just like a few extra, like a lot of extra dimensions.
Yeah, that's one of the things that makes string theory so mind-bending. Most versions of string theory require 10 or 11 dimensions to work mathematically, but don't worry, these extra dimensions aren't like the ones we experience. They're curled up really small, tucked away within the fabric of space-time.
So like little pockets of space that are too tiny for us to see.
Exactly. They're there, but they're hidden from our everyday perception.
Okay. I'm willing to entertain the idea of curled up dimensions, but is string theory the only game in town? What about loop quantum gravity? That's another one I've heard whispers about.
Ah, yes. Loop quantum gravity. That's another intriguing approach to quantum gravity. Instead of starting with strings, loop quantum gravity tries to quantize space-time itself. Imagine space-time not as this smooth, continuous fabric, but as a network of interconnected loops at the Planck scale, the smallest possible unit of distance.
So instead of smooth space-time, it's like the universe is pixelated at the most fundamental level.
That's a great way to visualize it. Loop quantum gravity has some promising features, like potentially resolving the singularity at the Big Bang, but it's still under development.
It's like the Wild West of physics out there. Speaking of the Big Bang, with all this talk about particles and forces and the fabric of space-time, it makes you wonder, how did it all begin? Where did all this stuff come from in the first place?
The Big Bang is our best model for describing the very early universe, that period of unimaginable density and temperature. But our current theories can only take us back so far.
So we're basically missing the first chapter of the universe's story.
For now, yes, the singularity itself, that point at the very beginning of the Big Bang where everything was concentrated into an infinitely small point, it remains a mystery. Our current theories just can't handle those extreme conditions.
It's like the universe is saying, that's classified information.
Maybe someday we'll unlock those secrets, but for now, we have to keep exploring, keep questioning. And speaking of exploring, let's talk about some of the most mysterious objects in the universe, black holes.
So with black holes, we're talking about a region of space-time where gravity is so intense it warps everything around it. Time slows down, light gets trapped. It's like a cosmic trapdoor, right?
That's one way to think about it. Even wilder is that, according to Einstein's theory of general relativity at the center of a black hole, there's a singularity.
A singularity. So we're talking about a point of infinite density. Like if you took all the stuff in the universe and crammed it into a space smaller than a pinhead.
It's definitely a challenge to wrap our heads around. And here's the thing. We can't actually see past the event horizon of a black hole.
The event horizon, that's the point of no return, right? Where even light can't escape.
Exactly. So whatever happens inside a black hole stays in a black hole. It's one of the biggest mysteries in physics.
It's like the universe has its secrets, and it's not giving them up easily. But haven't there been some incredible advancements in actually observing black holes? I'm thinking of those mind-blowing images, those blurry, glowing rings.
You're right. The Event Horizon Telescopes, a global network of telescopes all linked together. They basically created a telescope as big as the Earth.
That's incredible. And they were able to capture the shadow of that supermassive black hole at the center of our Milky Way galaxy.
It was a huge accomplishment.
I mean, it's one thing to talk about black holes, but to actually see those images, even if they're a bit fuzzy, it really hits home how much we still don't know.
That's the beauty of it, though, isn't it? Every new discovery just leads to more questions.
Speaking of questions, earlier we were talking about Feynman diagrams, those squiggly lines that represent particle interactions. It's like a secret code for unlocking the universe's secrets.
They're definitely elegant. And remember those virtual particles, the ones that pop in and out of existence. They're essential for mediating forces between particles.
It's like a cosmic dance floor where particles are constantly switching partners. But how can something that doesn't really exist have a real effect?
Ah, that's the magic of quantum mechanics. Virtual particles come about because of the Heisenberg uncertainty principle. It basically says that you can never know both the position and momentum of a particle with perfect accuracy at the same time.
So there's always some uncertainty, some wiggle room at the quantum level.
Precisely. And this uncertainty allows for tiny violations of energy conservation for extremely short periods of time.
So it's like particles can borrow energy from the universe as long as they return it quickly enough.
You got it. And even though we can't directly observe these virtual particles, we can measure their effects. One example is the Lamb shift, a slight shift in the energy levels of hydrogen atoms.
So even though we can't see them directly, their fingerprints are all over the quantum world.
Exactly. And it's not just the Lamb shift. These virtual particles are everywhere, constantly interacting and influencing the behavior of real particles. It even makes the idea of a distinct particle a bit fuzzy.
Fuzzy particles. What's next? Fuzzy math. But seriously, are you saying that particles are constantly exchanging these virtual particles with their surroundings so they're not really separate entities?
That's the idea. In quantum field theory, the lines get a bit blurred. It's all interconnected. Even seemingly empty space, what we call the quantum vacuum, isn't really empty at all.
You're blowing my mind here. Are you saying that even empty space is teeming with these virtual particles popping in and out of existence?
You got it. It's a constant dynamic dance. And here's the kicker. These fluctuations in the quantum vacuum can actually have measurable effects. The Casimir effect is a great example.
The Casimir effect. Tell me more.
So if you take two perfectly smooth plates and put them really close together in a vacuum, there's actually a tiny force that pulls them together.
Wait, a force in a vacuum? Where is that coming from?
It comes from those virtual particles. The plates actually limit the wavelengths of virtual particles that can exist between them compared to the vacuum outside the plates. And that difference creates a pressure, a force that pushes the plates together.
So those virtual particles, even though we can't see them, they're actually pushing those plates together. It's incredible how something so small can have such a noticeable effect.
It just goes to show that the universe is full of surprises, especially at the quantum level.
It definitely makes you realize that there's so much more to reality than meets the eye. But all this talk about particles and forces and the very fabric of space-time, it leads us back to that fundamental question, doesn't it? How did it all begin? Where did this universe, with all its strangeness and beauty, come from?
The ultimate question. And while we have the Big Bang model, which describes the evolution of the universe from a very early state, that very first moment, that singularity, is still a mystery.
It's like the universe's origin story has a missing prologue.
Exactly. Our current theories simply can't handle the extreme conditions of that first moment.
So we've got this incredible cosmic drama, but we're missing the first act.
It's true. But think about all the amazing discoveries we've made so far. Who knows what incredible breakthroughs the future holds?
That's the beauty of science, right? There's always something new to discover, something new to learn. It's a journey without end.
Precisely. And that's what makes it so exciting.
Well, that was quite a journey. From those early models of the universe with Earth at the center to the mind-bending world of quantum mechanics and black holes. This deep dive has been incredible.
It's amazing, isn't it? The more we learn about the universe, the more we realize just how much more there is to discover.
And for our listeners who want to go even deeper into these fascinating topics, I highly recommend checking out Hidden Unity in Nature's Laws. It's a wonderful exploration of these concepts and more.
It's a great read.
So until next time, keep those questions coming and never stop exploring the wonders of this incredible universe we call home. This is The Deep Dive, signing off.